A real-time system works as a loop. The external environment of the system gives information with which the real-time system has to compose. To do so, it first needs to acquire the information from the environment. Then, it has to analyze and treat it. And finally, act accordingly. That last action, however, changes the environment and thus restarts the loop. Take the example of a drone flying toward an obstacle. It has first to acquire sensors data to see the obstacle. Then, it treats the information by calculating the trajectory change. And finally, it transmits the order to its hardware to operate this change. But there is a time limit, a deadline, that has to be respected to keep the drone alive. A debugger is a tool that allows to stop the execution of a program and analyze what is happening when you have a problem. But it doesn't stop the time. Take a real-time task that has a start and a deadline. It thus has a duration limit d to do its work. But if you add a breakpoint, even if it only takes you x units of time, you now have a duration limit d minus x for a real-time task to do its work. With a tracer, however, you will not stop your task, you will save an event instead. To explain what a tracer is, take the case of a plane. If a plane crashes, it is common to use the flight recorder to know what were the last sensors values, the last discussions between the pilots, etc. It allows people to know what happened that led to the crash. A tracer is kind of a black box for computers. You can instrument applications and systems by using trace points. When the application runs, it will save execution events without interruption. If your task crashes, you can analyze the generated trace and see the last events. Like the flight recorder for the plane, you will know what happened, what led to the crash. And by knowing that, you will be able to find and apply a solution. To understand a little bit more how a tracer works, let's look at lttng-UST. We use three elements: the random access memory, the application, and the consumer. Consider that our application has a trace point cat. Each time we reach this trace point, a cat event will be stored in the buffer. And when the buffer is full, the application will contact the consumer via a control pipe to ask it to empty the buffer and save the events in the trace. But this schema wasn't optimal for high-performance real-time tracing. The write to the control pipe was creating a priority inversion and thus adding latency. We thus thought of a way to remove this control pipe, using a timed buffer reading. And without the write in the pipe, the priority inversion did not appear anymore. To compare our proposal to the standard usage, we had to improve real-time testing tools and methodology before using them on Linux kernels configured and optimized for real-time. Where we had 35 and 82 microseconds latency for pre-M30 and standard Linux kernels, we now only have 6 and 7 microseconds. With our work, lttng can now do low latency and high performance tracing, and thus trace real-time systems.